And next is Peter Eckert from EPFL.
No. Okay. So, yeah, hi. If you're as jet-lagged as I am, I will keep it quite short and hopefully interesting. I will tell you a little bit about what I did in my PhD, and my PhD was all about agility. And agility with very small robots. So why actually do we care about agility? Nature has actually shown us that agility is everywhere where there is fast motion. And actually, nature achieves agility right from the start. So you have this goat toddler that is just falling and crumbling everywhere all over, but it's doing that incredibly fast and already in a very, very good motion. It's recovering from a lot of perturbations. It's just amazing to me. And that was my big motivation to understand what is agility and how to achieve it. The understanding part we did in an agility definition and additionally an agility benchmark, which I will not discuss here because of time, but you're welcome to come to me and do that later, a bit offline. And I will talk a little bit about the robots that we developed during the project. I'm talking about we because all these robots, of course, were not possible without a lot of people involved. So every column here is one robot that we built, and then all the different parts that you actually need to make a robot move. I'm starting there from the beginning in our lab. We were starting from cheetah cub with these pantograph legs. If you don't know what these are, please come to me later. Which show amazing stable behavior, and they are super safe. These robots are super small, which makes them also not so powerful. That's a downside, but they're very safe to handle. So you can give that to a student after half an hour of training, and you don't have to worry that they will hurt themselves. They don't get killed like by these guys. Then we went on and we wanted to research a bit the influence of spines inside these small robots. So this was work that I started in my master thesis, continued then there. Here we leveraged the advantage of having small robots by doing very quick experimentation. So with these 3 robots, I did about 800 runs in about 1 month. The problem there is as they are not very precise in the production, so you have kind of a lot of delays, you get not so good repeatability in the results. But nevertheless, you can modify them very easy and they're very cheap. So these cost about 2K Swiss francs, 2K dollars. But they cannot be a sensor carrier. I have to hurry up because I only have 5 minutes, so I'm going fast. Next one that we built was Cheetah Cub AL, the improved version you see here. This controller, what you see there on the right running, was about half an hour after the robot first started running. So very intuitive, very fast iterations on the real hardware. If you want to then do something more sophisticated, you can do that also by putting sensors on the robot, doing some reflex control, doing some feedback control on it. But the problem here is actually for all this feedback, you need sensors that actually tell you what the robot is doing. And in this really small size, it's really difficult to find the parts off the shelf. So for example, for the leg position sensors, we had to design everything by ourselves. So we could get the chip, but the rest was, again, development work. So you have to specialize a lot. This is a robot I will show you also in demo session, hopefully. With this one, we demonstrated in the direction of versatility that we can do actually a lot of different things with a very simple control scheme. So this is all open loop, foot trajectory following with the intelligent mechanics. And can do pretty much amazing stuff like open loop step downs, double step downs, falling down and continuing to walk and so on and so on. But that's not where we want to stop. So there's a little bit of future work with my colleague Bosching, who was in the lab for 6 months and is leaving now. One nice thing with these robots is you don't need many people to handle them. So actually, with one person, he could do a lot of experiments by himself, like kicking the robot, like pushing it, like shooting with a cannon on the thing. And you don't have to have enormously big setups. And with this and some failures that we constantly encounter when we are doing actually robotics. I ask you to ask me questions if you're up to it. Okay, thanks.
Who wants to ask a question? I think we have time for about one. Aaron.
You said that a lot of the issues with the small robots is that the hardware integration and there's just not parts for them. Do you think that there's issues that are these issues if you had 10 times the budget and engineering staff, would all of these issues go away, or are there some issues that are fundamental to the size or the morphology that aren't just sort of, oh, you need a better electrical engineer?
I get what you want to say, yes. Partially yes, partially no. So you can for sure do a lot if you have an engineering staff just dedicated to robot development. So if you have a company developing your robot, that's helping a lot for sure. Building small things is a trend nowadays. So everything's getting smaller. So component-wise, I think in 5 years' time, we will not have these issues anymore because we can find the right sensors, the right things, the right boards, the right motor controllers, and everything. We can find it in a size where it's actually suitable for a robot less than 5 kilograms. That I didn't say, but it's all less than 5 kilograms. Yeah, but when we, for example, did on Chilla, so the rough terrain one, that was 5 years ago. Not 5 years, 3 years ago, and there was no, for example, Maxon mini control boards. So we had to design that all by ourselves, right? All the communication for that all ourselves. So there definitely technical staff would have helped, yes. Would have saved time for real experimentation afterwards.
Very good. Thanks very much.
Okay, thank you.